well. So it's a great time to talk about MLOps and ML infrastructure. So MLOps recently gained a lot of attraction, and some people claim that MLOps is the future of machine learning. And yeah, that's a few words about agenda for today. So I would like to present a state of art of enterprise ML. I would like to talk about challenges while moving to production, and then a short case study coming out from our experience in wholesale banking advanced analytics, including best practices and tooling for MLOps. So a few words about us. As a DAP team, and a model management, we are focused on building the model management capabilities inside the data analytics platform. And in the end, there will be like a short demo for the tooling part, and you can basically reproduce the examples which will be presented using this GitHub repo. Okay, so talking about enterprise, machine learning has no value unless related to some business process. So about the use cases, literally hundreds of problems that ML can resolve. And here is quite recent study from Algorithmia presenting a different application of machine learning for different business domains. And that basically shows how business evolve over time and become more diverse in a context of machine learning products. So from most obvious one like the recommender system to the less popular ones like trying to build the long-term customer engagement using the AI. Um, uh, Here a little bit different perspective, but from the same research. So it becomes even more interesting if you look at the maturity levels. So here is the graph representing the state of enterprise adoption and success rate for machine learning projects. So going from the left, you can notice that a lot of them are on the early stage, and as we are moving to the right, it's going through the evaluating stage as to the production grade deployments, where we actually have like only 8% of the matured solution in production. And that highlights two things. The appetite to apply ML grows recently, and deploying to prod is a quite challenging task. So I will rephrase the popular statement that not every model survives the contact with reality, and ML is still more about experimenting. So it is expected to not deploy like 100% of the models to production. Now the different benchmark, it reflects a state of AI from any perspective you can imagine. It is coming from state of AI organization, and you can and it's really insightful. So the authors of this report notice a general trend in industry which focus on running models rather than just doing the research in ML. And it's emphasized the growing interest in ML operation by means of the fastest growing GitHub projects and traffic on the Google search for the term MLOps. So you can basically notice, for example, iterative DVC or Cortex Labs Cortex, which is essentially a solution, open source solution for deploying the models. And the insight is that MLOps is relatively new term here, and the interest is growing. So now a couple of slides on challenges while moving to production. So going quickly with the basics of continuous integration and continuous delivery. It is well-defined procedure for software development. it is quite mature, and it's about wrapping the automation around building the software products. So basically, you develop your code in your favorite notebook or IDE. You run the tests, merge it to the source code repository, and then essentially the CI/CD process would initiate a build and would take all of your code and create like a single assembly from that. And eventually that will be deployed on the target environment. So continuous integration is usually decoupled from the continuous delivery by the means of the different frequency and schedule of the process. And yeah, the artifacts that are built during the continuous integration phase uh, uh, are essentially deployed on the target environment. So once the build passes all the tests and all validations are in place, that artifacts can be promoted to the appropriate environment, like the production one. And that proved to be working and be effective way of structuring your project. And so traditional CI/CD process has been around for the decades. So why not to apply this within the landscape of data engineering and data science? So basically to adapt at different stages of ML project to fit the CI/CD process. Essentially, the switch is about, so when it comes to the code, development is centered around notebooks. We need to have ability to track experiments, runs, hyperparameters, metrics, different versions of these artifacts, and anything which is essentially the outcome of your run. For the build process, so machine learning pipeline is about training the model, which is going to happen at scale. And with your new model features and a set of hyperparameters, you can basically apply it effectively. As you have the process in place, you can basically, you could probably can then track your different model versions using the dedicated model registry. And that's about continuous integration. The outcome of the continuous integration is we are going to release the artifacts, which is the outcome of a typical CI/CD pipeline. But release in machine learning products could be a model. It could be like entire pipeline or kind of a Docker image or entire code, depending on what is required on a downstream side. So for continuous delivery, while talking about data engineering or data science pipeline, the goal is to schedule regular jobs. On the other hand, that can be also a real-time serving, so doing the real-time predictions. The last step is about operations, which are even more complex, but I will be talking about it on the next slide. So a lot of things can be leveraged from the software engineering, but with additional complexity on top. So traditional programming is quite predictable and testable. We can verify our requirements on the code side, while machine learning has this property of having unclear success criteria. So basically, data scientists working to set up the objective functions and scores which needs to be evaluated. And there's this, there are these nice Google papers. I will present the link in the next slide. That states that ML systems have this special capacity for accumulating technical debt, because all of the maintenance problems of the traditional code plus having an additional set of ML specific issues. So the debt exists more on a system level rather than the code level. So referring to the major complexities, so machine learning is a data-driven approach, and data influences the ML system's behavior. And these are the things which were mentioned by Google. This paper have a couple of years, but I think it's still quite valid. So just to name a few of these complexities, For example, entanglement. So that means that no input is ever really independent. So changing anything actually changes everything, like changes in prediction. Um, the second thing is about data dependencies, which cost more than the codependencies. Uh, that can we can think of the unstable data dependencies. So the input features are unstable. We expect to have data drifts which occurs over time and happen in an implicit manner. Um, and yeah, that data may come from the different systems which may be corrupted. The other thing is underutilized data dependencies. That that means we can have like a legacy features, and this redundant features can go undetected for the process. We can have a bundled features, so features which are bundled together and possibly including the one which has no value or just add a little value to that, or the correlated features. Uh, that's about it. And there's also this kind of the anti-pattern, which is called the dead experimental code paths, to perform experiments with alternative methods as a conditions within the main production code. And the cost of this on the experimenting side is not so big, but on the surrounding infrastructures that needs to be reworked. And the last part, which is actually my addition to that, is lack of explainability. So explainability essentially bring confidence and value to clients. It express how the model works, and is a major way to debug it. And there's European Parliament published. So European Parliament just published a draft regulation on AI, and it also includes the explainability as kind of a requirement. Okay, so imagine that that iceberg represents our analytics platform, and our clients, so data scientists, most of the time care mostly about the tip of this iceberg. So all the other parts should be essentially transparent for users. That means that, okay, we have a platform. We are limited to the available data in the platform. So the process of getting access should be painless as possible. There should be like a quick way to get the computing resources, and that should support some kind of a declarative API. You need to structure your code as a machine learning pipeline, and need a way to orchestrate that also in a transparent way. And you basically need a scheduling capabilities over here. And yeah, as a data scientist, you are working in a team, so you need a collaborative tools basically to track the work you are doing, and kind of versioning capabilities of your artifacts to provide reproducibility of your experiments. And yeah, most of the time data scientists don't care about deployment, and yeah, it's yeah, we need to think about the way to automate this process. And in the end, there is this work done by the data scientists. So it's about the feature engineering, and in the end, it's about the modeling things. So you choose your favorite library and describe it in your experiments in terms of a Jupyter notebooks or some Python code. Okay, so how that is perceived by the data science communities? There is no silver bullet for the ML projects. So a lot of things happening around. There is this question in the center of the slide from the data scientists asking about secret weapons which could probably simplify their work. So on each stage, you would expect like a different functionality to be available, which requires different skill sets. So some people try to create kind of a general catalog for different machine learning tooling. You can find this link below. And yeah, here it is, our case study in wholesale banking advanced analytics. I would say we are still early stage adapters, but the graph presents our way to MLOps, where the ultimate goal is to deliver our products to customers faster. So we start with the basic design of our experiment. Then we would like to track our runs, hyperparameters, models, and scores with MLflow. I will be talking about the details of this tooling in a minute. And then from this notebooks, we move to the structured pipelines using Kedro. And on this stage, we need to validate the model. So we need to compare the accuracy, precision, choose the best performing model, and push it to model registry. And apart from actually the model registry is also provided by the MLflow. And apart from the release artifacts, it can also contain the data quality reports. So there is this nice library from my colleagues from WBAA, which is called Popmon. It is open source and available through the GitHub, so I encourage you to have a look on that. So we essentially want to create this report as the artifact inside the model context. For the release part, we expect to freeze our model, so assign it a version and release it as a Docker container or Helm chart, as we are working on the Kubernetes environment. Basically, we are cloud native, and that can be also like just a serialized model with the metadata stored in some shareable way. Then we apply the 4 I's principle, get approval from manager, and promote our model through the GitLab CI/CD pipeline. It's not yet in place, but we are still working on that actively. Then on the operations side, we essentially deploy it as a Kubernetes resource to do the real-time predictions and explanation, or deploying that as an ML pipeline for batch scoring. In the end, we would like to test our model with the production traffic, monitor the performance, detect data drifts and concept drifts. And as a last part, as our model is on production, we can make this model to be discovered by the other people in organization by using the Apache Atlas and Amundsen on top of it. I will be talking also about it in a minute. So essentially, it's about how much data scientists should care, or how much infrastructure should care. As you can see, like, this is the collaboration of different peoples, and basically we need to provide a split responsibility, so to let people do their job. So let's take a closer look on the tooling part, which is presented here. MLflow. That is two major components. MLflow tracking server. It provides the capabilities of reproducible experiments, trackable runs, and while you are doing the model training, and all the metrics, artifacts, and scores. And the second component is model registry as a service to register, version, stage, and promote your models. So MLflow to rule them all. It provides the portability, so being able to share artifacts between team members and support multiple flavors of your model, like TensorFlow, like sklearn, and basically the most popular one. It also supports different serialization formats. The basic functionality is a pickle file, which is quite general, but we also think about MLLeap as another level of indirection for serializing the model. So we support this idea to try something locally inside our platform. So from user session, we would like to provide opportunity to promote your local model to the collaborative MLflow instance. That basically is the instance which is used by the entire project, by the entire team. Yeah, and you have to be aware that Databricks open source that, but there are certain restrictions about MLflow. There's no multi-user and no user management in the community version. Basically, you need to provide it by your own. For the machine learning pipelines, yeah, so Jupyter Notebooks is not a great place to structure your ML code. So we would like to, so we actually leverage the Kedro framework to wrap our ML code into a pipeline. So that structure ML pipeline is built around the basic abstractions, which is called a node in Kedro. On the left, you can see the actual visualization of Kedro pipeline using the Kedro CLI and Kedro Vis library. There's also a data catalog available to track the state of your pipeline on different stages, and you can basically rerun only the certain nodes of the entire complex process. You can actually export your Jupyter notebooks as the nodes of Kedro. And there is also a nice template engine, which is called Kedro Starters, and we are building the custom ones for our needs. Unfortunately, I don't have a time to present the demo part, so I will just skip that one and move on. The last thing is that Kedro also provide the deployment part, so you can basically export your pipeline as a Airflow DAG, and this gives us opportunity to schedule our process in an automated way. It also supports the integration with Kubeflow. On the operational side, so we deploy the model for the real-time predictions, and so what we expect here is to just pick the existing model and deploy it with one click with declarative API to parameterize it. So Seldon Core is which is available as a Kubernetes operator. It's a bunch of services and custom resource definitions crucial to make this deployment automated. So it is a serving layer for our model. So we expose this model as a service. It also provides a ability to do the A/B testing through the shadow deployments on productions. And additionally, it gives us a model explainability with a Seldon Alibal library, which supports multiple state-of-art interpretability algorithms. And on the operational side, we basically monitor. We would like to monitor that also on the Kubernetes environment. So Seldon Core provides set of components for data drifts, concept drifts, and outlier detection. It provides the basic capabilities to monitor your models in action. And this anomaly detectors can be run as a standalone models. So there's kind of a unified interface, and it also provides the Prometheus exporters. And the last part, which I'm quite excited of, is ML governance and discovery. So many organizations suffers from lack of visibility over the ML assets delivered by the different teams of data scientists. And such model catalog would improve the collaboration within the organization through a single interface to discover available data and ML resources and related metadata. So different kind of the metadata can be recognized at various stages of the ML projects. And Atlas is designed for the ML governance, but not for the ML discovery. And Amundsen on top of Atlas is a way to provide a catalog of ML assets. And this is particularly interesting as being the Apache Atlas contributor, and so I also created the recently the RFC to support this ML entities discovery in Amundsen. You can basically have a look on that discussion. So to wrap it all, this is our roadmap. Some of these components are already working, especially the one which are mentioned on the exploration side. And there are multiple dimensions for this architecture. So we are moving from the explorations to operations, where the different compliance rules and risk applies. So essentially, we are moving from the data to the model. And yeah, so for the exploration part, we would like to provide as a part of the platform to a way to validate according to recent standards, to make a feature extractions already there, supported with the Jupyter notebooks. You can do the actual training and model evaluation with the support of the MLflow tracking UI and model registry. And then we are moving from this notebook to the structured pipeline. So KEDRAW is also available on the exploration side. And this gives us opportunity to schedule our process in an automated way, which can be integrated with Airflow. So then we are moving to the operational side. So we actually want to promote model or artifacts with the metadata. And for the deployment part, there's this idea to use Seldon for the real-time predictions and Airflow for the batch scoring with monitoring performance capabilities. And yeah, it is all applicable for the production usage and essentially all open source, with a bunch of integration required. So all of these components can be considered as a cloud native, and the basis is the Kubernetes platform. In general, it's not about hiding the infrastructure, but give the combination of tools to navigate this complex landscape of infra components by means of reducing the timelines, ensure reproducibility and scalability. So MLOps is here to remove our excuses not to deploy.